I, Dr. B. Shanmukha, Assistant Professor, Department of Mathematics, PAC, Mandya. Today, I discuss the topic on complex variable. First, I would like to introduce a complex number. The complex number is the real and imaginary part of a complex number z is equal to x plus iy or x and y respectively, and we write this complex number as real part of z is equal to x and imaginary part of z is equal to y. And every complex number we may represent in a polar form like z is equal to r into cos theta plus I sin theta, which is in polar form of the complex number, and where x is equal to r cos theta, y is equal to r sin theta, and r is called absolute value and theta is the argument of z. That is, we can express z is equal to r into e power I theta. That is, if you take a modulus of this z, modulus of z is equal to r into modulus of e power I theta. We know that modulus of any complex number is a square root of a real part plus square of a imaginary part. Therefore, modulus of e power I theta will become 1. So, mod z is equal to r and argument z is equal to theta. Geometrically, this representation mod z is the distance of the point z from the origin in the complex plane. So, that is by ordinary triangular property x is equal to r cos theta and y is equal to r sin theta. This could be expressed like this: mod z is equal to square root of x squared plus y squared, where r is equal to square root of x squared plus y squared. So, once we find that distance of a point in a complex plane, we can find the distance between any two points in the complex plane. So, say distance between 2 points z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2. Now, I take the difference of these two complex numbers z1 minus z2 can be taken as a simple representation x1 minus x2, y1 minus y2 is a complex number. And as we have learned in the previous slide that modulus of z is just a square root of x1 minus x2 whole squared plus y1 minus y2 whole squared. From this observation, we have to find equations and inequalities of curves and regions in the complex plane. For that matter, I have to consider this relation, that is mod z minus z naught is equal to just a real number r, where z is equal to x plus iy is any point and z naught is equal to x naught plus iy naught is a fixed point and r is a given real constant in the complex plane. And this I can express that mod z minus z naught is equal to r means any complex number can express in the form of a polar form also, that is just z minus z naught is equal to r into e power I theta. Suppose if theta varies from 0 to 2 pi, that is represented in this simple figure, that we can see that in that process we use the property of properties of modulus that gives the square root of x minus x naught whole squared plus y minus y naught whole squared is equal to r. So, squaring on both sides we get x minus x naught whole squared plus y minus y naught whole squared is equal to r squared. And observe that this equation is just a equation of the circle center at the origin, center at the point x naught y naught with radius r. Therefore, equation 2 represents a circle C of radius r with center at a point x naught y naught in the Cartesian form actually. Hence, equation 1 represents a circle C center at z naught with radius r in the complex plane. So, we obtain that equation of the circle in the complex form that is mod z minus z naught is equal to r, and it is in the Cartesian form x minus x naught whole square plus y minus y naught whole square is equal to r square. Consequently, from this we have the following results. From this we can construct some complex set and regions. So, first one is I have taken this one, that the inequality mod z minus z naught less than r. Mod z minus z naught less than r means you take any point in this area z and take a difference between that point and the center point z naught. If those values is less than r, holds for any point z inside C of the circle. That is, mod z minus z naught less than r represents set of complex points lies entirely inside C, or we can also say that it is an interior point of C. Such a region is called a circular disk, or more precisely open circular disk or open set. So, therefore, open circular disk and open set formed by this mathematical expression. This mathematical expression, so we can also write in this form: set of all complex number S is equal to Z such that Z minus Z naught, which is less than R, if that entire this set of complex number represents as a open set in the complex number set. Suppose if this in that circle R is very small, say I can take the delta greater than 0, no matter how small but not 0, then modulus of z minus z naught less than delta is called a neighborhood of the point z naught. Here just we go back to this one, we see that here if I take that R is small, very small, that means that you can take the delta greater than 0 of this one, means then I can get just a simple neighborhood of this point. So, therefore, we can construct that neighborhood of the point is having the property that with radius is a smallest distance, and that set of points forms a open disk in a smallest neighborhood point of the z naught. The inequality of that mod z minus z naught less than or equal to r holds for any z inside and on C. So, in that case we have to take that even the points on the circumference and inside the point. In that case we have taken that this region is called a circular disk or a closed set. So, circular disk or closed set, sometimes we can also take that consists of interior of C and C itself, that means on C itself. Now, one more inequality from this here, the inequality mod z minus z naught greater than R. It is very simple that all the points lies outside this region which are exterior of this circle, and those points we have taken as z on this area. That is simply we can take that z and take a distance between z and this point, center point z naught. Definitely it is greater than the radius of this circle. So, such points are exterior point of this inequality. And one more inequality which is very useful in solving the problem in complex variable, the inequality R1 less than modulus z minus z naught less than R2 represents a region between two concentric circles. Region between two concentric circles means this area, circles C1 and C2 of radii R1, R2 respectively, where Z0 is the center of circles. Such a region is called an open circular ring or annular region, and this region is annular region. In this annular region, we have to take, we can define a function because all the points lies in this region only. Suppose if z0 is equal to 0, then modulus of z is equal to r. Then that is what we have known, that z0, if it is there, modulus of z minus z0 is equal to r represents a circle of center, the circle of radius r with center z0. Then if z0 becomes 0 means, then this represents circle of radius r with the center at the origin. So therefore this represents circle of radius r with the center origin in the complex plane. And from this we can have these following consequences. Like if I take the value r is equal to 1, means radius is equal to 1, we have this following observations. That is, the equation mod z is equal to 1 represents the unit circle of radius 1 with the center at the origin. The unit circle means that we know that radius is always equal to 1. So from this case I can generate that open disk, but this open disk is represented by this mod z less than 1 represents open unit disk. So this open unit disk, and then mod z less than or equal to 1 represents the closed unit disk. Now at this stage students become familiar to construct that equation and region of curves in the complex plane. So now we pass on to the complex variable. So for that we have discussed about that complex number. Just by taking this parameter we can construct that complex variable. If x and y are real variables, then z is equal to x plus iy is said to be a complex variable. Said to be a complex variable, and all the properties what we have discussed, that just we convert it into the variable property, then we can construct a open disk, closed disk, all the properties. Then complex function we can define like this: if to each value of a complex variable z in some region of the complex z plane, there corresponds one or more values of w in a well defined manner, then w is a function of z defined in that region. Region means sometimes the region is also known as domain, and we write w is equal to f of z for each value which is mapped on to the point w by the well defined manner, w is equal to f of z. So this is a complex function property. Then in this case that we have seen that the complex function, if I define, means then the real and imaginary part of this complex function, how this takes this form. For example, that any function w is equal to z square, we can take that in the Cartesian form. If I take that x plus iy whole squared, then this gives that x square minus y squared plus I into 2xy. That means for each values of z we have this formation. This we can represent it in the case of complex function w is equal to u plus iv. Similarly, in the case of polar form, we can get that r square into, that is r e power I theta whole squared. This gives that r square into cos 2 theta plus I into r squared sin 2 theta. Then both the case you have to observe, this is function of r and theta, and this is function of x and y. So therefore in the complex function, w is having that real part and imaginary parts, that is u and v, which are depends on x, y in the Cartesian form, that and r and theta in polar form. That means u and v are functions of x and y in Cartesian form. Therefore w is a function of x comma y u of function of x comma y and v of x comma y in the Cartesian form, and in the polar form u r comma theta plus I into v r comma theta. So therefore, the complex variable, the real and imaginary part of a complex function w is equal to f of z u plus I v or u and v. Once we have defined function, then we can find out a limit case. Because this function is defined means, then we have to see that how this limit exists in this complex function. A complex valued function f of z is said to have the limit L as z approaches to z naught, except perhaps at z naught. This is very important concept that to be included in the definition. And if for every positive real number epsilon greater than 0, no matter how small but not 0, we can find a positive real number delta greater than 0 such that modulus of f of z minus L less than epsilon whenever modulus of z minus z naught less than delta for all values z is not equal to z naught. Or simply we can say that limit z tends to z naught, f of z is equal to f of z naught. That means as z approaches to z naught in the z plane, then we can find out that the two quantities f of z and L, as the distance between these two, f of z is as close as to the value of L when this z and z minus z naught are very sufficiently very small. In that situation, we have to see that except perhaps at z naught means, because function f of z is defined at every point, means very simple example, that is w is equal to log z or 1 by z. These two functions, simple function, we can take that log z is not defined at the point x is equal to z is equal to 0. So therefore, except perhaps at z naught, except at this point origin, this log z is defined everywhere in the complex plane. So this limit we have taken that this z as means the z approaches to z naught, which forms a open disk. Open disk means it is a neighborhood of z naught. We can also get that the corresponding open disk in the complex w plane. And we have two planes, that is, one is z planes for every values of z having x and y values will be mapped onto the values of u and v, because u and v are functions of x and y. So therefore, we need to construct that one more plane, that is w plane, to get that relations of w is equal to f of z. Z tends to z naught means that z approaches to z naught through independent path. So in this case, I just mentioned, if I take the z here, z naught, we have to approach z means there are all the direction we can approach to z naught. So that means I have taken that path 1. Path 1 means path along the x axis or along path parallel to the x axis. In that situation, here you have to first I have to take that y is equal to 0 and x approaches to x naught. From this path, we have to take that the path along parallel to the y axis. In that case, we have to take that x is equal to 0 and that y approaches to y naught. So this way we have to find out this limit of the complex variable z approaches to z naught. So this very simple example, we have to take that the z ball as limit z tends to 0, that is z bar divided by z. That means you can take that limit z tends to 0, x minus I y divided by x plus I y. Then along the path 1, I have to take that y is equal to 0 and x approaches to 0. That is, this gives, in that case, limit z tends to 0, z bar divided by z is limit x tends to 0, x divided by x, that is equal to 1. and the other case, that path 2, and the other case, in the path 2 means path parallel to the y axis, that is and we can take that x is equal to 0 and y approaches to 0. In that case, limit z tends to 0, z bar divided by z is equal to limit y tends to 0, that is minus I y divided by I y, that gives minus 1. And as limit property says that, so in all the independent of path means that both the way limit should be unique, but here that in both the way the limit is not unique, therefore limit does not exist in that case. So just to mention this, while solving the problem we have to use more this concept. Then limit exists for a defined function means then we can find out a continuity of a function f of z. A complex function w is equal to f of z is said to be continuous if at a point z is equal to z naught. At a point z is equal to z naught, if f of z naught is exists and limit z tends to z naught, f of z is equal to f of z naught. The function is defined at the point z naught, and as well as that limit must exist. So you limit exists means then you know that that independent of path that z dash to be approached to z naught, then you must have that unique value in all the directions. And also note that if f of z is said to be a continuous in any region R of the z plane, if it is continuous at a very point of that region. So it is similar that a function is continuous in an open interval means it must be continuous at a very point in that open interval. Suppose if you take that region, those region we have discussed just now, that suppose the region is a closed disk or open disk or any type of the region, in that case then at every point in that region this function must be continuous, otherwise this function is not continuous in that region. So then the derivative of a function f of z, we have that definitely a complex function f of z is said to be differentiable at z is equal to z naught if limit z tends to z naught, f of z minus f of z naught divided by z minus z naught exists and is unique. Unique means in all the direction, that from the limit is independent of path, therefore in all the paths the z approaches z naught means this limit must be unique. This limit is then called the derivative of f of z at z is equal to z naught and denoted by just f dash z naught is equal to limit z tends to z naught f of z minus f of z naught divided by z minus z naught, or f dash z naught is equal to limit z tends to z naught f of z plus f of z naught plus delta z minus f of z naught divided by delta z. This is happened that because of then delta z is equal to z minus z naught. If I replace setting delta z is equal to z minus z naught, then this becomes z naught plus delta z minus f of z naught divided by delta z. This is a actual definition of derivative of a complex function. And if the derivative is exists for a complex function, for any complex function, so we can prove that one theorem that is known as Cauchy's Riemann equations theorem. That is, theorem is that necessary conditions for the derivative of the function w is equal to f of z to exist for all values of z in a region R. One must have dou u by dou x, dou u by dou y, dou u by dou x, dou u by dou y are continuous functions of x and y in R. And second one, dou u by dou x is equal to dou u by dou y and dou u by dou y is equal to minus dou u by dou x. the relation 2 are known as Cauchy's Riemann equations, or simply briefly we can say that CR equations. So the proof is by the following way: if f of z possesses a unique derivative at any point z in R, then at any point f dash z is equal to limit delta z tends to 0 f of z plus delta z minus f of z divided by delta z. And this is the proof of this is in Cartesian form. We have denoted this, we have represent this function like this. In the Cartesian form, f of z is equal to u of x comma y plus iv of x comma y, and the delta z we have taken as delta x plus I delta y, and f of z plus delta z is equal to u of x plus delta x y plus delta y plus I into v of x plus delta x y plus delta y. Therefore, we have a function that is f dash z is equal to limit delta z tends to 0 f of z plus delta z minus f of z divided by delta z. Simply transform all these parameters here, then it is limit delta z tends to 0, that is you can take that u of x plus delta x and y plus delta y plus I into v of x plus delta x plus y plus delta y plus delta y minus u of x comma y minus, that is plus I into v of x comma y, and this is divided by delta x plus I delta y. So now we have to rearrange this one, because we have to rearrange that along with the real and imaginary part of this. We can get one expression. From that we can derive this. This is equal to limit delta z tends to 0, and it is u of x plus delta x y plus delta y minus u of x comma y divided by delta x plus I delta y plus this imaginary part I have to take here, that is u v of x plus delta x y plus delta y minus v of x comma y. Then I can write like this, that is divided by delta x plus I delta y. Open this bracket. Now we have to take that the limit delta z tends to 0 means we have to take that this limit like this. Z is any point in the complex plane. Take that the delta z this point. Now this approaches will be the path independent of path. Then I can take that along the path this one first, for which we can take the delta y is equal to 0 and delta x tends to 0. And for this approach take that delta x is equal to 0 and delta y tends to 0. This is the point P of x comma y. This is the point Q of x plus delta x and y plus delta y. So then this point is obviously, that is x plus delta x y, and this is obviously x comma y plus delta y. So, if I just by let us consider the limit delta z tends to 0 along the path parallel to the x-axis, along the path parallel to the x-axis for which delta y is equal to 0, then delta y is equal to 0 means that property that I have to taken that this as star or 1 according to that. If I use this case, then we can get that limit delta z tends to 0 means that will become delta x tends to 0. Now, along the path parallel to the x-axis, delta y is equal to 0 and delta x tends to 0. So, replace delta y is equal to 0 and approach delta x tends to 0. That gives u of x plus delta x y minus u of x comma y, that is divided by delta x plus I into v of x plus delta x and y, because delta y is 0, minus v into x comma y, that is divided by delta x. Here we see that it is similar to the derivative of the partial functions keeping y as constant and allow to vary x. Therefore, this is a partial derivative. As limit delta x tends to 0, then u of x plus delta x comma y minus u of x comma y divided by delta x is nothing but that partial derivative of u with respect to x as delta x tends to 0. That gives, that is partial derivative of dou u by dou x plus I into dou v by dou x. This is f dash z. Therefore, I have to take this one as 2 for this case. Now, similarly, you have to apply, that is, let us consider the limit delta z tends to 0 along the path parallel to the y-axis for which delta x is equal to 0 and delta y tends to 0. If that is the case, then the above expressions gives this following formula, following term that we have to taken, and that gives, this is limit delta z tends to 0. That is, I can take that second case from this first case we have to taken, that is f dash z is equal to limit delta y tends to 0. I can take that x comma y plus delta y minus u of x comma y divided by I delta y, because delta x is equal to 0 here. Therefore, I have to take this one I into v of x comma y plus delta y minus v of x comma y, then that is divided by I into delta y. I into delta y. You can take that this form. Now, here I and I get cancels. This is 1 by I is retained. And here as limit delta y tends to 0, observe that in the numerator u of x comma y plus delta y, here we are allowing to vary y and keeping x as constant. Therefore, it is a partial derivative of u with respect to y as delta y tends to 0. That gives 1 by I into dou u by dou y plus dou v by dou y. So, this gives f dash z is equal to, or I can write that f dash z is equal to minus I dou u by dou y plus dou v by dou y, that is 3. The existence of the derivative f dash z must that equality of that expression 2 and 3. If this equation 2 and 3 must be equal, otherwise this f dash z is not exists. The existence of f dash z must requires that equality of 2 and 3. must requires equality of 2 and 3. Therefore, I can take this equality and then you can see that what is that we are going to get that is equal to minus I into dou u by dou y plus dou v by dou y. So, if these two are equal means now equating real and imaginary part from this relation, we get this following relation, that is equating real and imaginary parts, we get that is dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. I equate this one, dou u by dou x is equal to dou u by dou y, but I have to written in this form. Then these are the actual CR equations, and this must be a necessary condition for f of z to be differentiable or derivative function, and that further the proof is given in clearly here, that all the things I have written already. Now this is equating real and part, we can get that this one, and the necessary condition of this the derivative existence, we have taken this one. The necessary condition for the derivative of the function w is equal to exist, we have to have these conditions should be satisfied. And now we have to define analytic function. A complex function f of z is said to be analytic at a point z is equal to z naught if it is differentiable at z naught as well as in a neighborhood of the point z naught. A complex function f of z is said to be analytic at a point z is equal to z naught if it is differentiable at z naught as well as in a neighborhood of the point z naught. That is the very important concept. The function f of z is not only a differentiable at a point, it must be a differentiable in the neighborhood of that point, every point in that neighborhood of that point, then only we can say that that function is analytic function. An analytic function is also called a regular function or an holomorphic function. So that analytic function means it is also a differentiable function in the complex analysis. Therefore, the above theorem we can use this analytic function definition, and then we can say that the theorem like this: if f of z is equal to u plus iv is analytic at a point z is equal to x plus iy, then u and v satisfies the Cauchy Riemann equations. Dou u by dou x is equal to dou u by dou y, and dou u by dou y is equal to dou u by dou x at that point. So proof is similar to the above theorem. It is just by taking f of z is analytic means that f of z possesses a unique derivative at that point. So proof is similar. And one more observation here is that a complex function f of z to be analytic, that the necessary conditions must be that CR equations must be satisfied by real and imaginary part of the complex function. So therefore, this is one more the thing. The proof is similar to that previous theorem, the derivative theorem. Now Cauchy Riemann equations in polar form we need to consider. The polar form that we also show that the polar form of Cauchy Riemann equations are dou u by dou r is equal to 1 by r into dou u by dou theta, and dou u by dou theta is equal to minus r into dou u by dou r. Now the Cauchy Riemann equations in Cartesian form we have proved, and then this is also very simple way we can prove this. This is similar to the problem. That is, Cauchy Riemann equations in polar form is as follows. then in the polar form that I have to take that z is equal to r into e power I theta. Then you have to consider that w is equal to f of z, and w is having real and imaginary part which are functions of r and theta in the polar form, and functions of x and y in the Cartesian form r I theta. We can take this one as this one. Now this is ordinary, using ordinary differential property, derivative property, we can differentiate this one with respect to r. Differentiate 1 with respect to r, that we gives dou u by dou r plus I into dou v by dou r is equal to, derivative of it is it's a function, that is chain rule we have to use, that f dash r into e power I theta into derivative of r into e power I theta, that is e power I theta, because derivative of r with respect to r is 1 and e power I theta is keeping as theta is a constant, therefore e power I theta as the constant term. Then differentiate this with respect to, that differentiate 1 with respect to theta partially, that is dou u by dou theta plus I into dou v by dou theta is equal to f dash of r into e power I theta. Then differentiate this with respect to theta, means r into derivative of e power I theta is e power I theta, and differentiation of I theta is just I. Now from 1 and 2 we have the relation. So from this case I can replace this from 1. So therefore using 1 on RHS of 2, we get dou u by dou theta plus I into dou v by dou theta, that is equal to, then r into I, that is I r, then f dash r e power I theta is just, it is dou u by dou r plus I into dou v by dou r, and this is, now consider, then multiply this r inside the I r, we get plus I into dou v by dou theta is equal to I r dou u by dou r minus I square is minus 1 and r into dou v by dou r. Now equating real and imaginary part, equating real and imaginary parts, we get dou u by dou theta is equal to, minus r into dou v by dou r, and dou v by dou theta is equal to r into dou u by dou r. This I can rearrange this one, therefore dou u by dou r is equal to 1 by r into dou v by dou theta, and dou u by dou theta is equal to minus r into dou v by dou r. So these are the CR equations in polar form. The CR equations in polar form is this one, and CR equation in Cartesian form is the previous